Hello everyone, good morning. How are you? Can you see the screen? Is my screen is visible and I am audible? Yeah, okay. Thank you for responding. Ayushi, hi, how are you? Yeah, okay. So today's session topic is what our solid state. This chapter is from physical chemistry and it is very, very important from the point of view of understanding how the solids are. Okay, how the molecules in the solid form are arranged. Their arrangement is in which type, how many molecules are present. Okay, how we can deduce different solids. There are two types of solid, crystalline as well as amorphous solids. Okay, there are so many important topics in this given chapter, and we are going to start from a very important topic from the solid state, that is what Bragg's equation. Right, so this Bragg's equation tells us about the simple relationship between the wavelength, that is lambda, and it tells about the wavelength of the X-rays, which is used to determine the interplanar distance between a crystal present in a given solid state and the angle of reflection. So this is what the interplanar distance, D is what the interplanar distance between the planes of the constituent particles present in a crystal, and theta is the angle of reflection. Okay, so this is our Bragg's equation. This is very, very important. So sometimes problems are asked in which sometimes D is given, theta is given, and you need to calculate lambda. Or sometimes lambda is given, theta is given, and you need to calculate D, that is interplanar distance. Okay, lambda is a wavelength, angle between X-rays and the plane of the crystal is theta. D is the distance between planes of the constituent particles, the distance between the planes. If our solid molecules consist of several planes like this way, if it is consist of several planes. Okay, so the angle of incident and angle of reflection. Okay, like this way, the X-rays are going to bombard on a given planes of a given crystal, right? This equation is applicable for determining the structure of given solids. Okay, and we can determine the structure of a given solid by doing this method, by doing the X-ray diffraction method. Again, the structure of certain complex substances like proteins and nucleic acids are also determined by using this method. Very nice. So now, most of the time, what happens is that we have given the length and we have given the angles, and we have to determine what will be the system present, which type of solid system is present there. So crystal lattice are of several types. They are around 7 type of crystal lattice: cubic crystal, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. So these are the several crystal lattices. Okay, so there are total 7 crystal lattices which can be tabulated along with their age, length, and their interfacial angles. These are the lengths, these are the angles, and there are certain examples also. Sometimes what happens is NaCl is of which type of crystal. Okay, so it is what cubic crystal. Sometimes NaCl is a is a crystal which has length A is equal to B equal to C, and angle alpha is equal to beta is equal to gamma is equal to 90 degree, which is this system. Okay, sometimes name also, example also given, and the lengths and age are also given, and we need to find which system is this. Okay, so this was very simple. This is a cubic system. What about tetragonal? One age length is not equal. Okay, but all the angles are equal. Their example of this is rutile, that is TiO2. Next, orthorhombic, all are not equal, but the angles are equal. Okay, and the examples is what? Ixomite. Next, monoclinic, not all lengths are not equal. 2 angles are equal. One angle is not equal to 90 degree. This is the gypsum. Next, not equal edges, not equal. What? This is the most अनसिमेट्रिक मॉलिक्यूल दैट इज ट्राइक्लिनिक, वहां पे कुछ भी सिमेट्री नहीं है, ठीक है। एंगल्स भी तीनों डिफरेंट होते हैं, एजेस आर आल्सो डिफरेंट। द एग्जांपल इज व्हाट K2Cr2O7। नेक्स्ट हेक्सागोनल, फॉर हेक्सागोनल the difference is what, one of the angle is what, 120 degree, right? Remember this. And the example of this is SiO2. And rhombohedral, edges are equal, but all the angles are not equal to 90 degree. They are equal, but they are not equal to 90 degree. And the example for this is what, calcium carbonate, that is calcite, right? Any doubts in this? So this is very, very important chart. You must remember this, okay? You can make the short form of for this CTOMTHR and remember this, okay? Remember the lengths and as well as the angles, very, very important from the point of view of our competitive exam, okay? Next, so when we talk about the crystal lattice, there are certain unit cells which are combined together to form a bigger crystal, like I have shown here in the first slide. Okay, here there are certain crystal lattices which are combined together to form the compounds. Here also. Okay, so which are those crystal lattices? Unit cells. So unit cells are of three types: simple unit cell, face-centered unit cell, and body-centered unit cell. What is the difference between them? What is the difference between them? So the smallest group of lattice point, which when repeated in all direction, we get the entire lattice, and the smallest can be simple cube, that is at the corners only the atoms will be present. At the corners only the atoms will be present. The particles are present only at the corner of the cubic cell, and that's why it is known as a simple cubic cell. When one of the atom is present in the center, it is known as a body-centered unit cell. And when at each face of a given cubic unit cell, at each face, so this is one face, okay, this is another face of the cubic unit cell, this is another face. So at each face, when at the center extra particle is present for each face, okay, how many faces are there for the unit cell? For the cube there are 6 faces, and at each face one particle is present. So that's why if for every face how much it is going to contribute, it is going to contribute half, okay. And here I have taken 8 molecules at the corners, okay, 8 corners. So that's why here 1 by 8 into 8. So total number of particles, how many present? Total number of atoms per unit cell are 4. Here simple 8 corners, 1 by 8 contribution of each atom. That's why overall how many number of atoms are present per unit cell? 1. Here 1 is present inside. That's why it is contributing to overall the cell. And 8 are present at the corner, and at that corner they are contributing 1 by 8. So that's why total number of atoms per unit cell are what? 2. This is very simple. Simple cubic unit cell, then FCC, and then BCC. Right? You know this. Very good. Next. So there are certain voids present. Even though the unit cell is composed of the particles, there are certain voids present in the given unit cell. These voids can be of 2 types. One is a 2D type of voids, and another are the 3D types of voids. So what are 2D types of voids? When there is a what? Simple triangular space in case of 2-dimensional packing, like this way. So there are 2 layers only, okay, 1 and this is 2. So when such arrangement is there, see here triangular void has been created, and this triangular void is what? 2D type of void. Okay, this triangular void is what? 2D type of void. Here you can see what has happened. Tetrahedral void and octahedral void has been formed during the 3D overlapping or 3D arrangement of given atoms. So what is 3D arrangement? So this is on one surface, 1, 2, 3, and on that another arrangement of the atoms has been arranged, and with this there is a formation of tetrahedral. So you know the tetrahedral molecule, like 3 are at the base and 1 at the top. So when like that way we arrange the atoms, okay, present, then particles, then you can see that inside there will be production of a void, and that void is nothing but tetrahedral. Okay, next octahedral void. Here 6 atoms are surrounding that given void, and that's why this there is a double triangular void. It's surrounded by here 6 spheres or 6 particles or 6 atoms, and that's why there is a production of or formation of octahedral void. When we talk about the void size, now you can see that octahedral void is of more larger size than tetrahedral and then the trigonal. Okay, please remember this. Next, when we talk about the cubic packing, this is what CCP. CCP means what? Cubic crystal packing. Here, the number of octahedral voids are 4 and the number of tetrahedral voids are 8. This is very, very important. Okay, how you are going to find out how many number of tetrahedral as well as octahedral voids are present in a given CCP or HCP? Okay, hexagonal closed packing, cubic closed packing. Okay, closed pack. So there are n spheres in the packing. Okay, in general for CCP and HCP, if suppose there are n number of atoms present, if suppose there are n number of spheres or atoms or ions are present in the given packing system, then number of octahedral voids are what? N, and number of tetrahedral voids are what? 2n. Right? Number of octahedral voids are n and number of tetrahedral voids are 2n. When we talk about closed cubic packing, it is referring to what? It is referring to what? FCC, BCC or simple cubic. What we are referring to it? Yes? Do you know this? Yeah? Can you tell me? Yes? Can you tell me? Okay, see here. Can you tell me? I am waiting for your answer, okay? Yes, next. You can see here, what is there? Simple cubic. Yes, simple cubic. I have determined the packing fraction. Okay, I have determined the packing fraction. And here I have written the radius of every particle. Okay, so here see, for CCP means what? Whether it is a simple cubic, face-centered cubic or BCC, cubic crystal packing, CCP is what? Actually, CCP is FCC. Okay, there FCC type of lattice we are considering, unit cell we are considering. Okay, any doubt in this? Because it contains how many number of atoms? 4. Simple cubic contains how many number of atoms per unit cell? 1. BCC contain how many number of atoms per unit cell? 2. How you can determine them? I have shown the formulas also. Right? Here all the atoms are present at the corner. That's why they contribute 1/8 to 8 corners of a given cube, and that's why total atoms are 1. For BCC, 8 corners पे 1 atom present है, as well as 1 is present in the center. So this contributes 1 plus 1, there are 2. FCC में क्या हो रहा है? At each face there is a 1 atom present. That's why all atoms are present at the corner, plus at the at the faces also there are what? Atoms present. So how many faces are there? 6 faces, and that's why when you calculate this now, you get the answer 4. So 4 number of atoms per unit cell are present. For FCC, 4 number of atoms per unit cell are present. So here if n is equal to 4, how many are the octahedral voids? Octahedral voids are also 4. How many are the tetrahedral voids? They are 4 into 2, that is 8. Okay, so these are what? Our octahedral voids, and these are our tetrahedral voids. Any doubt in this? Do you understand this? Okay, let's move on to the next. What are the important formulas? So for simple radius and the age, A is what? The lattice unit length. Okay, it is what? The length of the unit cell. R is equal to A by 2. The radius of a given sphere will be A by 2. And the total packing fraction is what? 52%. For face centered, how much is the radius? R is equal to A upon 2 under root 2. And the packing fraction is 74. For simple cubic, packing fraction is 52%. For FCC, it is 74%. And for BCC, it is how much? For BCC, it is 68%. This is again important. Okay, that's why I'm writing it, and that's why I have shown here. Okay, very, very important. Sometimes packing fraction is directly asked. How much is the packing fraction? If the atoms are arranged at the corners of a cubic unit cell and one atom is present in the center, means which type of crystal system is that? It is BCC type of crystal system. आपको डायरेक्टली नहीं पूछा जाएगा कि बीसीसी में पैकिंग फ्रैक्शन कितना है, आपको ऐसे पूछा जाएगा. बीसीसी का डिस्क्रिप्शन होगा, उसका पैकिंग फ्रैक्शन बताइए. You will given the options and you need to understand which type of crystal system has been given here, right? So 68% will be the answer. If we need to calculate the density for a unit cell, then this is the formula. D is equal to M, that is molecular weight of a given substance for which unit cell we are considering. Z is what? The number of atoms present. Na is the Avogadro's number, and A will be the unit cell length of that given unit cell, right? Next, there are certain ionic solids like rock salt, CSCl, zinc blend, fluoride, and antifluoride. And in ionic solids, how is the arrangement of the atoms present? So rock salt is actually FCC arrangement. We can also call this as closed cubic packing. FCC is also known as CCP. Please remember this, okay? And it has a coordination number Na plus. All Na plus are surrounded by 6 Cl minus ions, and all 6 Cl and all, sorry, 1 Na plus will be surrounded by 6 Cl minus ion, and 1 Cl minus will be surrounded by 6 Na plus ion. Okay, that's why here coordination number of each is what? 6. What are those ionic solids? LiCl, AgF, AgCl, NH4Br. These are what? Rock salt type of solid, and these are having FCC arrangement, that is closed cubic packing, which have packing efficiency how much? 74%. Remember this, right? Next, CSCl is having BCC type of arrangement, which has 68% of packing fraction, and their coordination number are 1 CS ion is surrounded by 8 Cl minus ion, and 1 Cl minus ion is surrounded by 8 CS plus ion. So here coordination number of this CSCl is what? 8. Okay, CSCl is what? 8 is to 8. Here it is what? 6 is to 6. Next, you can see the examples here, very, very important examples I have shown here: CSCl, TiCl, TiCl. Next, zinc blend, which is having CCP, which is also known as FCC arrangement. Coordination number of Zn2 plus here is 4 and S2 minus is 4. This is 4:4 type of unit cell. Next, fluoride, CaF2 type. Here CCP arrangement is there. Here coordination number is different. For Ca2 plus it is 8, and for F minus it is 4. So it is having 8:4. Next, antifluoride. Here reverse of the fluoride structure, Na are having 4 coordination number. On the other hand, O2 minus is having 8. Okay? So this is all about the ionic solid. Remember करना है. अगर simply आ गया question तो आपको ध्यान में रखना है. This is the answer. Okay. Next, on applying the pressure, what happens is that this NaCl structure, which is having 6:6, the NaCl structure which is having 6:6 coordination, it changes to CSCl type of compound, that is what? 8:8 coordination. So when you hit NaCl crystal, its coordination number initially was 6:6, but because of heating, its coordination changes to 8:8. And reverse of this occur at high temperature. So यहाँ पे लिखना है हमको pressure और यहाँ पे लिखना है हमको high pressure, high temperature. Right? Very good. Next, radius ratio. This is again very, very important. So we can determine the shape of a given solid by determining its radius ratio. Okay, what is radius ratio? Radius ratio is the radius of the cation divided by radius of anion present in the given crystal lattice. Okay, so if it is less than 0.155, then the coordination number of a given unit cell is what? 2. Or for a given crystal is what? 2. The structure, if there are, since coordination number is 2, the structure will be linear. Examples here, simple example you can see for linear molecule. Okay, LiCl like that way. Since next is what? This is first, this second. If the radius ratio, the ratio comes in between 0.155 to 0.225, then the coordination number of the crystal system will be 3 and its structure will be planar triangular. Example is given B2. Next, if it is in between 0.225 and 0.414, then the coordination number of the crystal lattice is 4 and it is tetrahedral in nature, and the examples are given here. If it is in between 0.414 to 0.732 in this range, its coordination number is 6 and it is octahedral, that is NaCl, you can say NaBr, KBr like this way. Next, if it is between 0.732 to 1, then its coordination number is 8 and it is cubic in system. Okay, its structure will be cubic structure, and examples are CSCl and CSBr. So this information is again very, very important. Okay, make a table, make a chart of the solid state. There are certain charts in this. Okay, आपको वो determine, आपको वो अच्छे से लिख लेना है, आपको ध्यान में रखना है. ठीक है, हम लोगों ने वो क्रिस्टल सिस्टम का अल्फा बीटा गामा एजेस एंड एंगल्स वाला एक चार्ट देखा, वो आपको रिमेंबर करना है, ये आपको रिमेंबर करना है. ठीक है, this is very important and this also very, very important. coordination number क्या होंगे, right? Next, there are certain defects. Even though the atoms are arranged carefully, there are certain defects which are known as point defects, and these point defects are of two types. One are the stoichiometric defects, and another are the stoichiometric defects, and some are the non-stoichiometric defects. So, what are the stoichiometric defects? These are the defects in which there are the imperfections in the crystals such that the ratio of cation and anion remains same as that of their molecular formula. Okay, the way it is shown in the molecular formula, in that way only the cation and anion will be present, but still there will be certain imperfection in the crystal. So there are two types of such defects. One is the Schottky defects and another one are the Frankel defects. What are the Schottky defects? These defects are due to equal number of cation and anion missing from the lattice side. So here what happens is that from the given lattice side, what happens is cation as well as anion both are missing. Cation as well as anion both are missing. But if one anion is missing, one cation will be missing. So equal number of cation and anion are missing from the given unit cell lattice sites. Okay. Due to this, there is a decrease in the density of crystal. Since तो cation भी चला गया, anion भी चला गया, जो density थी crystal lattice की वो क्या होगी, कम हो जाएगी. Okay, so due to this there is a decrease in the density of the crystal. So this type of defect is found in highly ionic compound with their coordination number high, NaCl, CaCl, AgBr, etc. So these are the one type of defects. Another defects are Frankel defects, in which what happens is here is due to the missing of ions, usually cations. So Frankel defect में कौन से ions missing है, यहाँ पे सिर्फ cation mostly क्या होते हैं, missing होते हैं from the lattice sites. And what happens is that they do not go anywhere, but they occupy the interstitial site. So if here one cation is present, so ये remove हो जाता है and it goes into the interstitial site in the given crystal system. Okay, and due to this there will be no change in the density because वो atom missing नहीं हो रहा है, वो सिर्फ उसकी जगह बदल रहा है. ठीक है, it was present at the lattice site, but now it is present at the interstitial site, which has happened between the atoms. What is interstitial site? So if this is the atom, this is another atom, and this is third atom, so there is a formation of interstitial site here. So here that cation is going to sit in the given crystal lattice only. It is not missing. So that's why this is known as a Frankel defect, and due to which density there will be no change in the density of a given crystal system during a Frankel defect. Next, this type of defect is found in the crystal where difference in the size of cation and anion is very large. So see here AgBr, यहाँ पे भी AgBr है. So AgBr shows both type of defect. Yesterday only we have seen the problem. So AgBr shows both type of defects, Schottky defect as well as Frankel defect. Okay. Next AgCl is there. Okay, cation और anion के size में बहुत ज़्यादा difference होता है for Frankel defect. AgCl is another example. Then ZnS. Right? Any doubts in this? Are you understanding this? Okay. Next defects are non-stoichiometric defects, which arises when ratio of cation and anion due to their imperfection differ from their indicated molecular formula. So molecular formula में दिखाए गए के बजाय यहाँ पे रेशियो जो cation और anion का होता है वो डिफरेंट होता है. ठीक है, and this defect results into, there are two types of defect. One is the excess of metal atom or excess of non-metal atom. So here excess हो जाता है, excess of atom or excess of non-metal atom. So here see, if suppose negative ion may be missing from its lattice side, leaving the hole which is occupied by an electron. Suppose there is a unit lattice in which the negative side is what missing, and that negative side has been occupied by an electron, and that negative side has been occupied by a electron. Okay, this is our crystal lattice system. So thereby here यहाँ पे negative charge था वो चला गया और यहाँ पे क्या फॉर्म आया, इलेक्ट्रॉन आ गया, तो यहाँ पे negative charge को बैलेंस हो रहा है. That's why here maintaining the electrical balance by the electron. So this electron thus trapped in the anion vacancies are called F center. If such electrons are trapped in anion vacancies, ये क्या हो रहा है, anion चला गया था वहां से, उसके वैकेंसी में ये क्या हो गया, ट्रैप हो गया. It got trapped in the anion vacancies, and that's why such are known as what, F centers. They are known as what, F centers, because they are responsible for imparting color to the crystal. Yesterday only we have seen that NaCl shows F center, but it shows yellow color, right? So when एफ सेंटर फॉर्म हो रहा है, मतलब क्या हो रहा है, वहां पे इलेक्ट्रॉन इज गेटिंग ट्रैप्ड इनटू द अनायन वैकेंसी. Similarly, we have seen that there is a molecule which was that molecule which was showing violet color due to the presence of what, F center into that. ठीक है, so this is about the F center. F center मतलब क्या होता है, इलेक्ट्रॉन ट्रैप हो जाता है अनायन वैकेंसी में and it imparts the color to a given crystal. Next, doping. What is the doping? Doping means what? We can add small amount of foreign impurity in the host crystal is known as doping. And due to this doping, what happens is that the electrical conductivity of a given crystal increases. That is the importance of doping. Please remember the definition. Right? Next, there are impurity defects which are present in the ionic crystals that arises due to the presence of some impurity in them. Okay, so how you can say that impurities are present? Sometimes those impurities are partially implanted into that. Okay, for example, N type of semiconductor and P type of semiconductors. Okay, see, foreign atoms are present at lattice site in substitutional solids and at vacant interstitial sites in interstitial solid. So वो जो impurity होती है वो कहाँ पे present होती है, जो interstitial solid से वहाँ पे जो interstitial site से वहाँ पे वो present होते हैं. Okay, these defects are important in N type and P type semiconductors. So there are some semiconductors in which this type of impurity defects are actually prepared, okay, in order to increase the conductivity of a given solids. Next, how you can explain the electrical properties for conductors, insulators, and semiconductors. So what is the band theory here? So band theory means what? When in conductors, what happens is that conduction band and the valence band are very, very close together. There is no gap between these two bands. Okay, and here what happens is that there is no gap, no energy gap present between these two bands, or valence band is not completely filled. See here, what is there? So यहाँ पे नीचे valence band दिखाया मैंने, यहाँ पे you can see this is a valence band, and ऊपर this is what a conduction band. They are overlapping to each other. Okay, they are overlapping to each other. So therefore, electron can easily flow under the influence of electric field from the valence band to the conduction band. Electron can easily flow because gap ही नहीं है कुछ, ठीक है, easily वो electron क्या होंगे, अगर वो electron यहाँ पे होंगे तो they can easily go to the conduction band and they can conduct the electricity. Okay, so if there are non-metal like graphite is a non-metal, but it becomes a good conductor of electricity because of presence of free electron in its structure. Okay, and that's why it becomes a good conductor. Next, semiconductors, the gap between valence band and conduction band is very, very small here. Okay, and that's why what happens is conduction band, some of the electrons may jump from valence band to the conduction band and some conductivity is observed. तो ये जो gap है इन दोनों का, ये बहुत ही छोटा है gap है, लेकिन वो जो gap है that is small, and that's why electron can jump from the valence band to the conduction band. Okay, if we increase the temperature. Okay, so what are the two types of semiconductors? Intrinsic semiconductors and extrinsic semiconductors. And extrinsic semiconductors are of two types, N type and P type, which are what, dope type of semiconductors. Okay, so what is intrinsic semiconductors? These are the semiconductors which show electrical conductivity of semiconductors increases with rise in temperature. ये कौन से टाइप के सेमीकंडक्टर्स होते हैं जिनकी कंडक्टिविटी क्या होती है, इंक्रीज होती है अगर हम लोग टेम्परेचर इंक्रीज कर सकते हैं, सिंस more electrons can jump to the conduction band. Substances like silicon and germanium shows this type of behavior and they are known as intrinsic semiconductors. So if a given crystal system is made up of silicon or germanium, it can act as an intrinsic semiconductor. So what is happening here? There is a flow of electrons. So यहाँ पे देखो flow हो रहा है, यहाँ पे charges का flow हो रहा है, और इसके वजह से this is a good semiconductor. Next, extrinsic semiconductor here. We can increase the conductivity of silicon, pure silicon and germanium. जो इंट्रिंसिक सेमीकंडक्टर में हम लोग यूज कर रहे हैं वो मटेरियल को उनकी जो कंडक्टिविटी है we can increase by doping them with the elements of 13 group or with the elements of 15 group present in the periodic table. Such a type of conductance is called as extrinsic semiconductors, and there are two types of this. One is the N type and another one is a P type. So what is N type? In N type, what happens is silicon or germanium are doped with the group 14 elements. They are doped with the group 14 elements. Okay? Sorry, these are group 14 elements. These are doped with group 15 elements. ठीक है, हमको पता है बोरॉन है, बाद में कार्बन है और बाद में क्या है, नाइट्रोजन. So this is what 13, this is 14 and this is 15. Right? In doubt in this, तो कार्बन के पास आता है सिलिकॉन और जर्मेनियम. ठीक है, यहाँ पे आता है फॉस्फोरस, यहाँ पे आता है आर्सेनिक, यहाँ पे आता है एल्यूमिनियम और यहाँ पे क्या आता है गैलियम. तो इनको क्या करते हैं, अगर इससे डोप किया तो ये हो जाएंगे हमारे पी टाइप, क्योंकि यहाँ पे क्या होता है, एक यहाँ पे पॉजिटिव चार्ज इनके पास एक एक्स्ट्रा होता है, पॉजिटिव होल यहाँ पे होता है. पी टाइप में क्या होता है, दे हैव वन पॉजिटिव होल, नो इलेक्ट्रॉन, देयर इज अ होल हियर. बट इन एन टाइप व्हाट इज हैपनिंग, अगर हम इससे डोप करते तो एक एक्स्ट्रा हमारे पास क्या होता है, यहाँ पे निगेटिव चार्ज होता है which flows. Okay, and that's why it is known as n type of semiconductors. Okay, that's why it is known as n type of semiconductor. So these are what, p type and n type. 14 group elements are doped with 15 group, it is known as p type. If it is doped by 13 group elements, it is known as n type, n and p. Right? Any doubt in this? Okay, let's move on to the next. Insulator में क्या होता है, large gap होता है, that's why they cannot conduct the electricity. Next, magnetic properties of a given substances. So compound can be diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and perimagnetic, depending upon their behavior with the respective magnetic field. So diamagnetic substances are weakly repelled by the magnetic field and do not have any unpaired electron, and these are the examples. Paramagnetic substances कौन से होते हैं, जो attract होते हैं magnetic movement से, and they contains actually the unpaired of electron. Okay, these are the examples. Ferromagnetic substances means what, they are attracted by the magnetic field and they show the permanent magnetism present even in the absence of magnetic field, are known as ferromagnetic substances. Antiferro means they have magnetic moment 0 due to the compensatory alignment of magnetic moment. So यहाँ पे magnetic moment 0 होता है, उनको बोलते हैं antiferro. Peri means they have net dipole moment due to unequal parallel and anti-parallel alignment of magnetic moment. So these are the example ferrites. Okay, please remember all this. Yeah, so let's move on to the next. Let's solve certain problems depending upon this given solid state information. Now, which is the incorrect statement? Density decreases in case of crystals with Schottky defect. NaCl is insulator, silicon is semiconductor, silver is conductor, quartz is piezoelectric crystal. Frankel defect is favored in those ionic compounds in which sizes of cation and anion are almost equal, and FeO 0.98 has non-stoichiometric metal deficiency defect. So can you tell me what is the answer here? Yeah. ABCD for problem number 1, which is incorrect. We don't need to find the correct statement. We just need to find the incorrect statement. They can be 1 or 2. Yeah, can you tell me? So Frankel defect, पहला क्या है, डेंसिटी डिक्रीजेस इन केस ऑफ क्रिस्टल विद स्कॉटकी डिफेक्ट. दिस इज ट्रू स्टेटमेंट. हम लोगों ने देखा बोथ पॉजिटिव और नेगेटिव दोनों मिसिंग हो जाते हैं क्रिस्टल लैटिस से, इसकी डेंसिटी क्या होती है, डिक्रीज हो जाती है. दिस इज ट्रू. NaCl इज इंसुलेटर, सिलिकॉन इज सेमीकंडक्टर, सिल्वर इज कंडक्टर एंड क्वार्ट्ज इज पीजोइलेक्ट्रिक क्रिस्टल. यू नो NaCl इज इंसुलेटर. हम सॉल्ट खा रहे हैं रोज, कंडक्ट कर रहा है इलेक्ट्रिसिटी, नहीं ना करना. वेरी गुड. सो इट इज इंसुलेटर. सिलिकॉन इज सेमीकंडक्टर. वी जस्ट हैव सीन सिलिकॉन एंड जर्मेनियम आर सेमीकंडक्टर्स. सिल्वर यू नो Ag कंडक्ट्स इलेक्ट्रिसिटी. ओके, बट इट इज क्या, वो महंगा इसलिए हम लोग उसके तार नहीं बना रहे. ठीक है, बट इट इज अ गुड कंडक्टर, इट इज अ मेटल, इट इज अ गुड कंडक्टर ऑफ इलेक्ट्रिसिटी. Quartz is what, piezoelectric crystal. Okay, so this is again true statement. Next, Frankel defect is favored in those ionic compounds in which sizes of cation and anion are almost equal. So this is not true. Just we have talked that there should be vast difference between the size of cations and anion. That's why this is false statement. This is incorrect statement. This is our answer C. Next, Fe 0.98, Fe 0.98 has non-stoichiometric metal deficiency defect. So this is what? This is what? Non-stoichiometric defect due to metal deficiency shown by FeXO, where X is 0.93 to 0.96. So यहाँ पे Fe होगा 0.96 and O. FeO नहीं होगा. ठीक है? It is due to the deficiency of metal deficiency, not oxide deficiency, right? So that's why this is again not true. So हमारे options A, C और D क्या हो गए? हमारा correct answer हो गए. ठीक है? C और D are the incorrect statement present here. Next, in calcium fluoride having the fluoride structure, coordination number of calcium ion is Ca2 plus and fluoride ion R. So we have talked about this CaF2, What is the structure of it? It is having a fluoride structure. And we have talked that here in this structure, fluoride structure, Ca2 plus ions are in the FCC. Yeah, can you tell me? C answer, 8 and 4. Very good, Ayushi. Okay, so for Ca2, calcium fluoride ion or calcium fluoride molecule, there is a fluoride structure in which in this molecule, what happening is Ca2 plus ions are in FCC arrangement, and each Ca2 plus ion here is connected to 4F minus ion. Okay, and below it, ions below it, and to another set of 4F minus ions above it. Okay, so Ca2 plus ion, its coordination number is 8. On the other hand, F minus ion is having coordination number 4. So each Ca2 plus is surrounded by 4F minus above and 4F minus below. 4 above होते हैं और 4 below होते हैं. ठीक है, इस वजह से इसका ओवरऑल कोऑर्डिनेशन नंबर कितना हो रहा है 8. बट फॉर फ्लोराइड F minus ion, there are 4 Ca2 plus ions surrounded to each, and that's why its coordination number is 4. So here answer is 8 and 4. Very good, Ayushi. Yeah, you have given correct answer here. Next, lithium has BCC structure. Okay, lithium has BCC structure. Okay, next problem is what? Lithium has BCC structure. Okay, something is happening. Wait a minute. Okay. Yeah. Yes. So here lithium is having BCC structure. Its density is 530 gram per m cube, per meter cube, and its atomic mass is given. Okay, and its atomic mass is given. We need to calculate here what we need to calculate here. What is the A value? That is length of the unit cell. What is the length of the unit cell? So here you can see the answer. For BCC, we need to solve this problem. Okay, maths use करना है यहाँ पे. For BCC, you know how many number of atoms are present? BCC unit में कितने होते हैं? Atoms 2 होते हैं per unit cell. ठीक है, हमको डेंसिटी दी हुई है kg per meter cube में. ओके, एटॉमिक मास कितना है लिथियम का? दिया हुआ है 6.94 ग्राम पर मोल. वी नीड टू कैलकुलेट द एज लेंथ, दैट इज ए. वी नीड टू कैलकुलेट ए, दैट इज यूनिट सेल लेंथ. ओके, सो Na क्या है हमारा? एवोगाड्रोस नंबर यू कैन नो, एंड यू नो द फॉर्मूला फॉर डेंसिटी. डेंसिटी इज इक्वल टू Z इनटू एटॉमिक मास डिवाइडेड बाय Na इनटू A क्यूब. सो यूज करो ये फॉर्मूला. यहाँ पे डेंसिटी को हम लोगों ने ग्राम पर सेंटीमीटर क्यूब में कन्वर्ट कर लिया है. ठीक है, एनी डाउट इन दिस? राइट. नेक्स्ट हमको ऑप्शन में दिए है पिकोमीटर, ये ध्यान में रखना है. जेड की वैल्यू 2 पुट कर दी. एटॉमिक मास को मैंने लिखा है पर मोल, सॉरी एटॉमिक मास मेरे पास दिया हुआ है ग्राम पर मोल में, इसलिए मैंने डेंसिटी को भी ग्राम पर सेंटीमीटर क्यूब में कन्वर्ट कर लिया है. ग्राम पर मोल यहाँ पे आ जाएगा हमारा एटॉमिक मास. एनी नंबर ऑफ एटम्स, दैट इज एवोगाड्रोस नंबर, मल्टीप्लाइड इट बाय द डेंसिटी गिवन. ओके, दैट आई हैव कन्वर्टेड इनटू ग्राम पर सेंटीमीटर क्यूब. से यहाँ पे ग्राम ग्राम कैंसिल हो जाएगा. ओनली सेंटीमीटर क्यूब विल बी रिमन. मोल मोल भी कैंसिल हो जाएगा. मोल मोल यहाँ पे कैंसिल हो जाएगा. ओनली सेंटीमीटर क्यूब विल बी गिवन. सो दिस इज व्हाट A क्यूब. वी नीड टू फाइंड आउट A. टेक under root 3 cube of this given value. You will get the answer 352 into 10 raised to minus 10 centimeter, and 10 raised to minus 10 centimeter means what? It is in terms of picometer. So our answer here is what? B. For this you need to be more fast in order to solve the problem. देखो नीट के क्वेश्चन में आ गया है. नीट के क्वेश्चन पेपर में ऑलरेडी ये क्वेश्चन आया है. Just they will just change the values, yeah, and you will need to find out the answer. Okay, next problem, ionic radius of A plus and B minus ions are given. The coordination number of each ion will be. So आपको अगर कटायन का रेडियस दिया हुआ है और अनायन का रेडियस दिया हुआ है और आपको अगर कोऑर्डिनेशन, we have to use the chart, radius ratio वाला chart. Okay, we have talked about this. So see here answer I have shown radius ratio R plus by R minus. R plus दिया हुआ है, R minus दिया हुआ है, कितना आया? 0.5. ठीक है, 0.54. So this is in the range of what? 0.414 to 0.732. Hence here coordination number of each ion will be 6, and the compound of such type is what? NaCl. Right? So यहाँ पे coordination number each ion का कितना होगा? 6 होगा. ठीक है, आपको पता है ना, मैंने आपको चार्ट दिखाया था, याद आ रहा है? ये देखिए चार्ट आपको मैं दिखाती हूँ फिर से. तो हमारा आंसर यहाँ पे कितना आया? 0.54 आया. that is in the range of this. So what is the coordination number of each ion? 6. Structure is what? Octahedral. अगर वो इस रेंज में आता तो coordination number हम 8 बताते थे, अगर इस रेंज में आता तो coordination number 4 बताते थे, right? Okay, very good. Okay, next problem. Vacant space in BCC lattice unit cell is. So we know the packing fraction. If we know the packing efficiency of each, then we can determine अगर इतना पैकिंग है तो वैकेंट कितना है, 100 से माइनस करो. बीसीसी में कितना होता है, सिंपल क्यूबिक में आपको बताया मैंने कितना होता है 52, एफसीसी में कितना होता है 74, बीसीसी में कितना होता है बताया 68. अगर इतने परसेंट की पैकिंग हो रही है then 100 minus 68 कीजिए, कितना हो गया? ABCD, what will be the answer, guys? Yes, easy problem, very very easy problem. Yes, समझ में आ रहा है बात? पैकिंग इफिशियंसी 68 है, एम्प्टी स्पेस कितना बचा? 32%. वेरी गुड. ओके, वेरी वेरी गुड. या ओके, या आयुषी 32%. ऑप्शन इज सी. Next problem, the correct statement regarding the defects in crystal solid is Frankel defect decreases the density of the crystalline solid. This is not true. Frankel defect is a dislocation defect. Frankel defect is found in halides of alkaline metals. Schottky defects have no effect on the density of crystalline solid. This is again not true. ठीक है, डेंसिटी पे इफेक्ट हो ही रहा है. ठीक है, तो यहाँ पे हमारा आंसर क्या है? करेक्ट स्टेटमेंट कौन सा है? बी. Frankel defect is a dislocation of what? Defect of smaller ions. यहाँ पे क्या होते हैं, एक आयन उसकी जगह छोड़ के दूसरे साइड में चला जाता है. ठीक है, दूसरे जगह पे चला जाता है, तो ये क्या हो रहा है? डिसलोकेशन ऑफ आयंस हो रहा है. Here smaller ions are dislocated from their normal sites to interstitial sites. Frankel defect is shown by compounds having large differences in their size of cation as well as anion. Hence alkali metal halides do not show Frankel defects. That's why alkali metal halides do not show the Frankel defect. Also, Schottky defect decreases the density of the crystal, while Frankel defect doesn't decreases. That's why here correct statement अगर होगा तो वो होगा क्या? B. ठीक है. Next, a given metal crystallizes out with a cubic structure having H length. यहाँ पे हमको A का वैल्यू दिया हुआ है 361 पिकोमीटर. If there are 4 metal atoms in one unit cell, okay, atom कितने हैं? 4 है. What will be the radius of one atom? What will be the radius of one atom? So how you are going to calculate this? So we have talked about this simple formulas में आपको मैंने बताया था कि रेडियस आप कैसे निकालोगे. सिंस यहाँ पे Z क्या है? 4 है, तो ये क्रिस्टल लैटिस कौन सा है हमारा? FCC. नंबर ऑफ एटम्स आर व्हाट? 4. So this structure is what? FCC. So for FCC, what is the relationship between age length and the radius? This is the what? Relation. R is equal to A upon 2 root 2. So A का वैल्यू दिया हुआ है 361. पुट करो वैल्यू, कैलकुलेशन करो, आपको वैल्यू मिल जाएगा 127 पिकोमीटर. Right? Yeah, very good. Next problem. If A is the length of the side of a cube, the distance between the body centered atom and one corner atom in the cube will be. तो यहाँ पे भी हम लोगों को क्या निकालना है? डिस्टेंस निकालना है. ठीक है, so distance between the body centered atom and one corner of atom is how much? So ये हमारा अगर body centered में atom है, ठीक है, और अगर एक एटम हम लोगों ने यहाँ पे पुट किया है, ठीक है, यहाँ पे the distance between the body centered atom and one corner atom is. So यहाँ पे कॉर्नर में एक एटम है और ये बॉडी सेंटर, ये डिस्टेंस हमारा कितना होगा वो हमको फाइंड आउट करना था. तो वो कितना होता है? √3/2a, दैट इज हाफ ऑफ द बॉडी डायगोनल. ये जो बॉडी डायगोनल होगा हमारा, इसका हाफ. ठीक है. या नेक्स्ट, अ मेटल हैज FCC लैटिस. FCC लैटिस है मतलब Z क्या होता है? 4 होता है. समझ लो. द एज लेंथ ऑफ द यूनिट सेल इज दिस. एज लेंथ दिया हुआ है मतलब A का वैल्यू दिया हुआ है. डेंसिटी दी हुई है मेटल की, आपको मोलर मास निकालना है. सेम फॉर्मूला यूज करो डेंसिटी वाला. डेंसिटी इज इक्वल टू Zm अपॉन Na इंटू A क्यूब. Z दिया हुआ है 4, क्योंकि हमको इससे पता चला 4 है क्योंकि FCC लैटिस दिया हुआ है. कभी कभी Z दिया हुआ होता है, हमको क्रिस्टल लैटिस एज्यूम करना है. कभी कभी क्रिस्टल लैटिस दिया हुआ होता है, हमको Z उससे कैलकुलेट करना है. ठीक है, समझ में आ रहा है? So we need to calculate the molecular weight. So rearrange the formula density Na into A cube divided by Z. Do this calculation, you will get the answer 27 gram per mole. ठीक है, any doubt in this? Just rearrange the formula. Very very important formula. Very 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 important. Next, the number of carbon atoms per unit cell of diamond unit cell is. So in diamond, it is like a ZNS type of system. Okay, zinc blende के जैसे उसका structure होता है. Carbon forms CCC type of, that is closed cubic packing, which is what FCC, and also occupies half of its tetrahedral voids. ठीक है, वो जो tetrahedral voids होते हैं वो हाफ वो क्या करता है? प्रेजेंट होते हैं. सो टोटल नंबर ऑफ कार्बन एटम्स कितने हैं यूनिट सेल में? सो कॉर्नर में कुछ प्रेजेंट है मतलब FCC जैसे, कॉर्नर में कुछ प्रेजेंट है और एवरी फेस में कुछ प्रेजेंट है, ठीक है, फेस सेंटर्ड होने के कारण, और 4 जो टेट्राहेड्रल वॉइड है वहां पे वो प्रेजेंट है, क्योंकि टेट्राहेड्रल वॉइड कितने होते हैं हमारे, अगर n is what number of atoms, how many number of atoms are there, 4, n are the octahedral voids, that is 4, and 2n are the tetrahedral voids, right? These are the tetrahedral voids. कितने होंगे, 8 होंगे। लेकिन क्या है, कार्बन एटम कितने प्रेजेंट होते हैं, ओनली हाफ ऑक्यूपाई करते हैं। सो 8/2 कितने टेट्राहेड्रल वॉइड ऑक्यूपाई करेंगे, 4 एटम्स विल बी प्रेजेंट एट द टेट्राहेड्रल वॉइड। तो यहाँ पे आ गया 1 प्लस यहाँ पे आ गया 3 प्लस यहाँ पे आ गया 4। सो हाउ मेनी एटम्स आर प्रेजेंट, 8। How many atoms are present per unit cell? 8 atoms are present per unit cell. Very, very good question. Right? Any doubt in this? Next problem. A metal crystallizes with the FCC cubic lattice. The edge length is given. Diameter कितना होगा? तो यहाँ पर डायमीटर कैसे निकालोगे, रेडियस निकालो, रेडियस का डबल कर दो, आपको डायमीटर निकल जाएगा। एफसीसी में क्या होता है रिलेशन, R इज इक्वल टू A/2√2। आपको A दिया हुआ है, एज लेंथ दिए 408, कैलकुलेशन करो, 2 से डिवाइड करो, 144 पिकोमीटर आपको मिल गया। क्या, रेडियस, रेडियस का डबल कर दो, आपको मिल गया डायमीटर। वेरी गुड, राइट, वेरी इजी प्रॉब्लम। 288 ए ऑप्शन। नेक्स्ट, द नंबर ऑफ octahedral void per atom present in the cubic closed packing is, yeah, can you tell me the answer here? Question number 12, the number of octahedral voids per atom present in cubic closed packed structure. Yeah, if n number of atoms are present, then n number of octahedral voids are present. FCC में कितने होते हैं, number of atoms, CCP and FCC. Number of octahedral void is same as the number of atoms, that is 4, right? Any doubt? Next, structure of mixed oxide is cubic closed pack, that is CCP. The cubic unit cell of mixed oxide is composed of oxide ions. 1/4 of the tetrahedral voids are occupied by the divalent atom. Octahedral voids are occupied by the monovalent atom. Formula of the given oxide is. So this is very, very good question actually. So here number of atoms in CCP, that is cubic crystal packing, कितने होते हैं, 4 होते हैं, ठीक है। टेट्राहेड्रल वॉइड कितने हो जाएंगे फिर, 2 into n, that is how much, 8 हो जाएंगे, ठीक है, CCP में। नंबर ऑफ A2 प्लस आयंस कहाँ पे प्रेजेंट है, देखो 1/4 ऑफ द टेट्राहेड्रल वॉइड्स आर ऑक्यूपाइड बाय डाइवेलेंट एटम A, ठीक है। तो 1/4 जो है 8 टेट्राहेड्रल वॉइड में से 1/4 किसने ऑक्यूपाई किए, डाइवेलेंट एटम ने, मतलब कितने एटम्स प्रेजेंट है, 2 एटम प्रेजेंट, ठीक है। नंबर ऑफ ऑक्टाहेड्रल वॉइड्स, बाद में ऑक्टाहेड्रल वॉइड्स आर ऑक्यूपाइड बाय द मोनोवैलेंट एटम B। ऑक्टाहेड्रल वॉइड्स कितने होते हैं, नंबर ऑफ एटम्स, सो दैट्स व्हाई कितने प्रेजेंट होंगे, B प्लस आयन 4 प्रेजेंट होंगे। अगर A2 प्लस आयन हमारे पास O2 माइनस इज टू A2 प्लस इज टू B प्लस, तो ऑक्साइड कहाँ पे प्रेजेंट है, एट द CCP अरेंजमेंट, ठीक है। A2 प्लस कहाँ पे प्रेजेंट है, टेट्राहेड्रल वॉइड में, और B प्लस कहाँ पे प्रेजेंट है, ऑक्टाहेड्रल वॉइड में। तो 4:2:4, दैट इज व्हाट, 2:1:2। तो A, ये क्या है O, ये है A और ये है B, तो क्या हो गया स्ट्रक्चर, O2AB2, दैट इज व्हाट, AB2O2। सो व्हाट इज द आंसर हियर, ऑप्शन B। वेरी गुड क्वेश्चन एक्चुअली, समझ में आ गया सबको, बहुत स्टेप बाय मैंने आंसर किया है। डाउट? Okay, next. A solid compound is there, XY, has NaCl type of structure. If radius of the cation is this much, the radius of the anion will be, yeah. So here we need to find out the radius for anion. You know that for NaCl structure, वो NaCl जैसा है तो रेडियस रेशो कैसा होगा उसका, ऑक्टाहेड्रल मॉलिक्यूल के रेडियस रेशो क्या लेते हैं हम लोग, इन बिटवीन 0.414 to 0.732। तो मैंने ये वैल्यू ली है। अगर रेडियस ऑफ कटायन 100 है, रेडियस ऑफ अनायन कितना आएगा, इतना आएगा। सिंपल प्रॉब्लम, very simple formula. Next, AB crystallizes in a body centered cubic lattice with edge length A दिया हुआ है। The distance between two oppositively charged ions है, दो oppositively जो charged ions है उनमें का डिस्टेंस कितना होगा वो हमको यहाँ पे पूछा है। तो see here, AB crystallizes in body centered cubic lattice, तो यहाँ पे दिया हुआ है कि वो BCC lattice में हो रहा है फॉर्म, ठीक है। हमको डिस्टेंस निकालना है दो oppositively charged आयन का, मतलब प्लस कैटायन और अनायन का डिस्टेंस कितना होगा। सो R 2R + 1, 2 टाइम्स ऑफ R + R - इज गोइंग टू इक्वल टू √3/8। तो क्यों यहाँ पे मैंने इस तरह से किया, ये क्या है, एज लेंथ है, ठीक है। तो बीसीसी लैटिस में कटायन और अनायन का जो डिस्टेंस है वो कितना है, 2r + r - इज इक्वल टू √3/a। सो कैलकुलेट दिस, जस्ट ट्रांसफर द 2 हियर, यू विल गेट द आंसर 335 पिकोमीटर। सो ये फॉर्मूला हम लोगों ने बीसीसी के लिए देखा हुआ है ऑलरेडी, रेडियस इज इक्वल टू √3/a/2। दिखाया, दिखाओ फॉर्मूला, दिखाओ, देखो देखो रेडियस रेशो कहा गया हमारा, रेडियस रेशो या radius ratio, yeah, this is the formula for body centered cubic unit cell. What is the formula? √3/4a। ठीक है, तो √3/4a के बजाय हम लोगों ने क्या यूज किया, √3/2। या ओके, इन डाउट इन दिस? ओके, नेक्स्ट, लिथियम मेटल क्रिस्टलाइजेस इन अ बॉडी। यहाँ पे फिर से बीसीसी दिया हुआ है, लेंथ दी है हमारी साइड की 351, एटॉमिक रेडियस ऑफ लिथियम भी। तो सेम प्रॉब्लम है, लेकिन यहाँ पे सिर्फ हमको रेडियस निकालनी लिथियम एटम की। तो क्या होता है बीसीसी के लिए, देखो √3a/4 एज लेंथ। ठीक है, एज लेंथ हम लोगों को दी हुई है 351। जस्ट डू द कैलकुलेशंस, यू विल गेट द आंसर ऑफ रेडियस। यहाँ पे हम लोगों को दोनों का रेडियस निकालना था ना, कटायन और अनायन का, इसलिए मैंने इसको 2 से मल्टीप्लाई किया और √3 यहाँ पे हमारा आ गया है। ये 2 को बाद में मैंने नीचे ट्रांसफर करके आंसर निकाला। यहाँ पे हम लोगों ने डायरेक्टली रेडियस निकाला, सिर्फ रेडियस ऑफ कटायन निकाला। यहाँ पे रेडियस ऑफ कटायन प्लस अनायन, इसलिए 2 टाइम्स किया। नेक्स्ट, कॉपर क्रिस्टलाइजेस इन एफसीसी क्रिस्टल लैटिस विद यूनिट सेल लेंथ 361। एफसीसी है, यहाँ पे यूनिट सेल की लेंथ दी हुई है। व्हाट विल बी द रेडियस? सो यू नो फॉर एफसीसी व्हाट इज द रिलेशनशिप बिटवीन रेडियस एंड आवर एज लेंथ, a/2√2, a/2√2। so put the value, you will get the answer 128 picometer. That is option D. Yeah, that is option what? D. Next, percentage of free space in body centered cubic unit cells. So yeah, tell me कितना percentage free है? Free space, free, how much amount is free? Packing fraction कितना है? Same question repeat हुआ है, लेकिन आपको समझ में आया है क्या concept? Yes, yeah. What will be the answer here? Percentage of free space in a body-centered cubic unit cell is. So here is what? Packing fraction is 68%. So 100 minus 68. How much is that? 32%. Right? So D will be the answer. Okay. Right. Yeah, you should be. Yes. So क्या होता है packing fraction? The ratio of volume occupied by atoms in unit cell to the total volume of unit cell is called packing fraction. क्या होता है packing fraction? Ratio of volume occupied by atom to the total volume, or density of packing is, it is also known as density of packing. So for body centered, packing fraction is 68%, that is 0.68 of the unit cell occupied by the atom. So what will be the empty space? Empty space 32%. Yeah. Next problem, very easy. Which of the following statement is not correct? Which of the following statement is not correct? Not correct हमको ढूंढना है. The number of carbon atoms in a unit cell of diamond are 4. Number of Bragg lattices in which a crystal can be categorized is 14. Next, the fraction of total volume occupied by the atoms in primitive cell is 0.48. Molecular solids are generally volatile. So here, which is the not correct statement? So number of carbon atoms in unit cell of diamond is 4. So this is true. Okay. Number of Bragg lattices in which crystal can be categorized as 14. So Bragg lattices कितने हैं total? 14. ठीक है. 14 मतलब सिंपल में होते हैं जो हम लोगों ने 7 क्रिस्टल सिस्टम देखी ना, वो 7 क्रिस्टल सिस्टम हम लोग आगे डिवाइड करते हैं ब्रैग लैटिसेस में, ठीक है, और उनको हम कहते हैं ब्रैग लैटिसेस, और टोटल कितने होते हैं 14। फ्रैक्शन ऑफ टोटल वॉल्यूम ऑक्यूपाइड बाय एटम्स इन प्रिमिटिव सेल, सो सिंपल में कितना फ्रैक्शन ऑक्यूपाई होता है एक्चुअली 52%, दैट इज 0.52 नॉट 48, सो दिस इज रॉन्ग। सो वही हमको ढूंढना है नॉट करेक्ट, सो हमारा आंसर सी बराबर है। मॉलिक्यूलर सॉलिड्स आर जनरली वोलाटाइल, सो दिस इज अगेन ट्रू। Okay, packing fraction of cubic unit cell is like this way we calculate it. Okay, and it is how much? It is 52%, that is 0.52, and unit cell is occupied by atom. And how much is the एम्प्टी स्पेस 0.48। यहाँ पे जो उन्होंने ऑक्यूपाई बोला है ना, अगर ये फ्री स्पेस कहते तो ये बराबर होता स्टेटमेंट, लेकिन यहाँ पे उन्होंने ऑक्यूपाई बोला है, तो ये जो स्टेटमेंट है ये गलत हो गया है। दैट्स व्हाई अवर आंसर इज व्हाट सी, बिकॉज वी नीड टू फाइंड आउट द नॉट करेक्ट स्टेटमेंट, राइट? In doubt in this? Okay. With which one of the following elements silicon should be doped so as to give P type of semiconductor? So we want P type of semiconductor, right? P type of semiconductor चाहिए, मतलब उसमें क्या होना चाहिए? होल होना चाहिए। होल होना चाहिए मतलब अगर हमारा ग्रुप 14 का अगर एलिमेंट है, ठीक है, तो उसमें 13 का ऐड करना चाहिए या 15 का ऐड करना चाहिए? अगर 13 का हम लोग ऐड करते हैं तो होल क्रिएट होता है, राइट? और अगर 15 का हम लोग ऐड करते हैं तो वहां पे क्या क्रिएट होता है? एक निगेटिव साइड क्रिएट होती है एक्स्ट्रा इलेक्ट्रॉन होने के कारण। तो यहाँ पे हम लोगों को 13 ग्रुप का एलिमेंट ऐड करना पड़ेगा। 13 ग्रुप का एलिमेंट कौन सा है इसमें से? सेलेनियम, जर्मेनियम, बोरॉन एंड आर्सेनिक। या आयुषी, वेरी गुड। सो हियर आंसर विल बी व्हाट? बोरॉन। यस, हियर आंसर विल बी व्हाट? बोरॉन। सो सिलिकॉन should be doped with the element with group 13, that is group 3, B, boron, aluminum, gallium, indium or thallium of the periodic table. P type of semiconductor will be obtained. ठीक है, very good. Now next problem, the appearance of color in solid alkali metal halide is generally due to. So alkali metal halides में क्या होता है? हमको कलर देखने को मिलता है। मैंने कल आपको बताया NaCl का कलर क्या होता है? येलो कलर। तो कलर क्यों इंपॉर्ट होते हैं हमारे सॉलिड्स को? जस्ट वी हैव टॉक that due to the formation of F center. What is the meaning of F center? When anion get trapped into the, electron get trapped into the anion का वैकेंसी, ठीक है, अनायन था, वहां अनायन चला गया तो वहां पे वैकेंसी तैयार हो गई। तो वैकेंसी में जब इलेक्ट्रॉन चला जाता है, when electron get trapped into the anion vacancy, there is a formation of F centers and those F center impart color to a given crystal lattice. So F centers are, यहाँ पे आंसर क्या हो गया हमारा? ऑप्शन बी। एनी डाउट इन दिस? स्कॉटकी डिफेक्ट और फ्रैंकल डिफेक्ट की वजह से कलर इंपार्ट नहीं होता, इंटरस्टिशियल पोजीशन में जाने के कारण भी नहीं मिलता है, ठीक है। जब इलेक्ट्रॉन ट्रैप होता है अनायन वैकेंसी में तभी एफ सेंटर फॉर्म होते हैं, और तभी एफ सेंटर अगर सॉलिड कोई भी सॉलिड में फॉर्म हो गए तो वो क्या करते हैं? उस सॉलिड को कलर इंपार्ट करते हैं, ठीक है। F centers are the sites where anions are missing and instead electrons are present in those anions, and these are responsible for the color of a given solid, right? Any doubts in this? Yes? Any doubts anywhere? Hello? Okay, so thank you so much for joining in this session. If you have any doubts, you can tell me. Okay, no doubts. Okay, thank you so much for joining in. Let's meet tomorrow for the next session.